welcome to section 2.8, where we are discussing the derivative as a function. So in the previous section, we looked at evaluating the derivative at a specific number, at a fixed value, a, but we don't have to limit ourselves to only evaluating a derivative or an instantaneous rate of change, a slope of a tangent, at one single value. We can do it for any number of values along a function, and that's going to allow us to develop a formula for the derivative f prime of x, which is the limit as h approaches 0 of f of x plus h minus f of x all over h for any values of x at which the limit exists. This derivative function is in and of itself a function. So we can solve for it using the techniques we saw in the previous section, but we can also observe it as its own independent formula function in terms of x. So let's look at an example. If f of x equals x cubed minus x, find a formula for f prime of x, and then compare the graphs of f and f prime. So for part A, find the formula. So f prime of x is the limit as h approaches 0. So this is our f of x. So all these x's for this first part are going to get replaced by x plus h terms. So this is going to be x plus h cubed minus x plus h minus f of x. So minus just x cubed minus x all over h. Now, in order to algebraically simplify, we need to go ahead and expand all of this out. So we're going to have a long string of terms here. The cubic is going to give us, so we're going to have x cubed plus 3x squared h plus 3xh squared plus h cubed minus x minus h, and then distribute this negative, minus x cubed plus x all over h. We get some cancellation, not a ton, just the x cubed with the negative x cubed. And I believe that is it. Oh, here, and we also have this minus x and the plus x right there. So this gives us limit as h approaches 0. What do we have left? 3x squared h plus 3xh squared plus h cubed minus h all over h. Each of these terms has a factor of h in them, so we can factor them out and then cancel it with the h in the denominator. So we're left with 3x squared plus 3xh plus h squared minus 1. Substitute in 0 now for all of the h's. So those are gone, and we're just left with 3x squared minus 1. And this is our formula for the derivative of f of x, that function, x cubed minus x. And we could then use this derivative function to find that slope of the tangent at any x value we want. Now, if we treat this as its own independent formula, this own independent function, we can actually graph this alongside f, the original. So let's take a look at what that looks like. So here we have in blue is the original graph, the x cubed minus x. In green, we have the derivative graph, the f prime of x, 3x squared minus 1. Now, if you note the features that relate these two to each other, remember what the derivative is, so the green one. The derivative is the slope of the tangent line at any given point on the original function f, okay, or that instantaneous rate of change. So if we were to pick any specific point on this original graph, the slope at that point is the output on the green one. So, for example, like right over here, so somewhere around -1, 0. This has a positive slope. It looks like it's going up maybe a little bit greater than 1, almost 1.5 for its value, or 2 even. Yeah, maybe even 2. And if you look at the output on this graph, the output is actually, it's exactly 2. So the slope of this blue graph at that point is 2. So the output on this graph at that point is 2. If we look at like this point here, notice this is where a point where the graph changes direction. It levels off at the top here. It goes from a positive slope to a negative slope. So it actually has a slope of 0 right here at the top. This has a slope of 0 here, exactly where this graph has an output of 0. So if you look at the overarching behavior here, this graph has positive slopes here, 0, negative slopes here because it's going down as you go from left to right, 0, and then positive slopes again the rest of the way. If you look at the outputs on the green one, all of these outputs are positive here, right? Everything that corresponds to these. The output is 0 here, where it levels off. The outputs are negative down here, right? These outputs are in the negative region, while these slopes are going down. And then it turns back up, right? The outputs become positive again because these slopes became positive again. So we can look at the relationship between the two and read visually not only how the graph is changing, but how its slopes are changing as well. Let's look at a different type of example. We have f of x is the square root of x. Find f prime of x and then state the domain of f prime. So to find f prime of x, we're going to take the limit as h approaches 0 of the square root of x plus h minus the square root of x all over h. And of course, as always, this one is not suitable for direct substitution. We need to manipulate this in some way. Here we have a sum or difference of square roots of radicals. So we can use a technique that we saw earlier in chapter 1 of using the conjugate. So we can go ahead and multiply by the square root of x plus h plus the square root of x. And we have to keep it balanced, so whatever we do to the top, we have to do to the bottom as well. The whole purpose of the conjugate is that when you multiply this out, so you do first, outer, inner, last, like that, when you FOIL this out, the first is going to give us x plus h proper, right? Because the square roots will square and then they'll cancel. The last will give us the minus just x, right? Rad x times rad x. But the outside and the inside are exact opposites of each other, and so they end up canceling to 0. And that's the whole point. is that those middle two terms cancel. So we're just left with x plus h minus x all over h times that whole set of terms down there. So square root of x plus h plus the square root of x. We have an x minus an x. So just h over h times rad x plus h minus rad x. Those h's will cancel. So we have 1 over rad x plus h, plus, these should both be plus rad x. Now we can do direct substitution. So this is 1 over rad x plus 0 plus rad x. So that's 1 over rad x plus rad x. Or just 1 over 2 rad x. And that would be our formula for the derivative of the square root of x. So we create this new function. And because this is a new function, it has its own domain and range. So the domain of f prime of x, these are all possible x values that can be inputted into this function. Because it's in a radical, it has to be greater than or equal to 0. And because it's in the denominator of the function, it cannot be 0. So we're going to have everything from 0 to infinity, not including 0. Again, because it's in the denominator of a fraction. So the domain of f prime is slightly different than the domain of f, right? The original domain of f, you could have 0, because rad 0 is just 0. But this new result gives us a slightly altered version of the domain because of that fraction. Now, when it comes to looking at the derivative and using notation for the derivative, the f prime of x notation, while it is a very common one, is not the only one. So we have a few other notations here that we can see and encounter fairly frequently. Of course, f prime of x is very common. Y prime is just about the same as that. The other alternative that we usually use is dy dx. This is called the Leibniz notation. It's named after the guy who discovered calculus and started using that notation to begin with. The way that this one reads, so dy dx, it reads like derivative of y, so that's the dy, and then with respect to x. So the dx on the bottom here is telling us what the variable is within the function, just like this one does with f prime of x. Okay, you can also apply, derivative with respect to x of f like this. So this can be applied to entire functions, and this will be a pretty common notation when we're using it within functions like this. And then you can also have the capital D notation. We don't use this one quite as much at this level, but it's something that you can see from time to time. Now, when we're talking about the process of taking a derivative, the term that we use for that is called differentiation. We say that a function f is differentiable if f prime of a exists. In other words, if we are able to take a derivative, right, or able to differentiate the function. We say it is differentiable on an open interval, ab, if it is differentiable at every value in the interval. So if it's differentiable at every point from a to b, that means it's differentiable over the entire interval. Differentiability and continuity are actually related to each other. It turns out that if f is differentiable at a, then f is continuous at a. So this is something that draws a direct line between differentiability and continuity. So we can actually prove this using similar techniques that we've seen so far in this chapter. So to prove this statement, we're going to assume that f is differentiable, so it has a derivative that exists, and we're going to prove that f is continuous. So in order to prove that a function is continuous at a point, we need to show that the limit as x approaches a of f of x equals f of a, right? We need to prove that the limit exists, that the function exists, and that they are equal to each other. If we can prove this statement is true, using only differentiability as our only assumption, then we will have proven it. All right, so since f is differentiable at a, then that means f prime of a, which is the limit as h approaches 0, or excuse me, we're going to use the alternative version because I'm trying to get x approaches a in here. We're going to use limit as x approaches a of f of x minus f of a over x minus a. If you recall, this is one of the alternative formulas we have for the derivative. So since f is differentiable, this limit must exist because we're assuming that it's differentiable. Notice that f of x minus f of a, that term that we would have up here in the numerator, if we just look at this term by itself, this is exactly the same as if we did f of x minus f of a over x minus a times x minus a. So this is one of those situations in a proof where it's less important to understand, like, well, why would we know to come up with that? And just to understand the logic of it. So this and this are equal. They are the same thing, right? Because all we've done is we've multiplied by something and divided by that same thing. So these two technically form a 1, and they could just cancel at any time. We're not going to cancel them because we need them, but these two are equivalent. And this is going to help us in this process. Using the limit laws, we can take the limit as x approaches a of f of x minus f of a, rewrite this using this that we just saw. So this is the limit as x approaches a of f of x minus f of a over x minus a times x minus a. Using the limit laws, we can split this across the multiplication here. So we're going to get the limit as x approaches a of f of x minus f of a over x minus a times the limit as x approaches a of x minus a. Now, if you look at the terms that we have here, this is this, right? That is the formula for f prime of a. That is the derivative. So this is f prime of a times, for this one, if x is approaching a, that means that x minus a, the distance between them, is going to shrink, right? It's going to go towards 0, because if x is getting closer and closer to a, that means that this is getting closer. So we're going to have a minus a, which would produce a 0. And anything times 0 is 0. So now that we know that this limit is 0, let's take a look at the limit of f of x. So limit as x approaches a of f of x. This is equivalent to the limit of f of x plus f of a minus f of a. So this is another case of something that is true. If we can just follow the logic of that, right? These two are equivalent. You can add and subtract the same thing, and you haven't changed the identity of the formula. If we do a little rearranging, we get f of a plus f of x minus f of a. Split this up across the addition here. So we get limit of f of a plus limit of f of x minus f of a. Now, this first one, limit as x approaches a of f of a, that's just f of a, right? Because if x is approaching a, there are no x's in this at all. It's just a's already. So that's just f of a plus this one is this one. It's the one that we just saw up above, which we just showed was 0. So plus 0 equals f of a. And if you look at what we just showed that the limit as x approaches a of f of x equals f of a, which is precisely, back up here at the top, what we needed to prove to show continuity. So thus, the limit as x approaches a of f of x equals f of a as desired. So therefore, if f is differentiable at a, then f is continuous at a. End of proof. So differentiability automatically gives us continuity. However, it doesn't go both ways all the time. Just because the function is continuous does not mean it's differentiable. So the next question to ask is, what makes a function not differentiable? And there are three primary reasons. We have what we call corners, which we would define as a rapid change in direction. So that would be something like, if you have your graph here, something like this. So like right here at this tip, it goes from one direction, one slope, to immediately a different direction, a different slope. This is what we would call a corner. And this is a great example of something that is continuous, right? The function exists everywhere here, but is not differentiable at that point. Of course, discontinuities, right? If it's not continuous, it certainly won't be differentiable because, right, it's not even continuous there to begin with. So if you have, something like this where the graph breaks like that, this is not continuous and it's not differentiable. And lastly, vertical tangents. So something, if you have a graph that's going like this and it just drops straight down like that, it would not be differentiable here where the slope is perfectly vertical. Because remember, the derivative is the slope of the tangent line. So if the tangent line is perfectly vertical, the slope of that line is undefined, right? Because the slope of a vertical line is undefined, so the derivative would be undefined, or in other words, does not exist, or in other words, it's not differentiable. So these are some common examples of cases where you would not have differentiability. If we look at a more specific example, let's look at the absolute value function. Where is this function differentiable? So the absolute value function, of course, it's broken into two pieces primarily, right? You've got the negative section and the positive section here of that V shape. So we're going to break this into smaller pieces. So we're going to first consider x greater than 0. So the absolute value of x is x. So that's this piece right here, right? Just the line y equals x. So all the values will be positive for x. X plus h will be positive, which means that the absolute value of x plus h will just be x plus h. So our derivative at any point in this section would be the limit as h approaches 0 of absolute value of x plus h minus absolute value of x all over h. But again, because all of the values are positive on this section of the graph, right, this portion up here, these absolute values are not necessary. So we get x plus h minus x all over h. X's cancel. We have h over h, which is just 1. So we get that f is differentiable for any x value greater than 0, and specifically the derivative is 1. And remember, the derivative gives us slope, and this is a line, right? And the slope of this line is 1, so it makes sense. The derivative would be 1. Similarly, if we look at the flip side, so we're looking at the negative section of the graph over here, x is less than 0, so the absolute value of x is the opposite of x, because again, x here is negative, so the opposite of the negative becomes a positive. That's what the absolute value does. And this one becomes the opposite of x plus h. So we get our limit as h approaches 0 of absolute value of x plus h minus absolute value of x all over h. That's the limit of negative x plus h minus negative x all over h. We still get some cancellation here, so notice we get a negative x here and a positive x here. But this negative distributes, so we have a negative h over h, which gives us a negative 1. So f is also differentiable for any x less than 0, right? The derivative exists, and it is negative 1 at all of these values. But if we look at what happens at x equals 0, at this point in between the two where they meet, f prime of 0, if we substitute that in here, we end up getting absolute value of h over h, but the absolute value of h is different depending on which side you're coming from, right? Because if you're on the left-hand side, it's this line over here, and if you're on the right-hand side, it's this line over here. So we need to compute the one-sided limits. So if we compute the limit from the right, absolute value of h is positive, right? The h value is positive. So this is just going to be h over h, which is 1. Coming from the left, h is negative. So we're going to get negative h, just like we had up above. So we get a negative 1. Since these limits are different, f prime of 0 does not exist. So what this tells us is f is differentiable at all x except 0. Okay, and that's that corner that we talked about. Right? makes a rapid change from a negative slope to a positive slope at that single point. And if you look at the formula for the derivative, which I have written down here, the formula is also piecewise, just like the original absolute value function is. The derivative is -1 if x is less than 0, and it's 1 if x is greater than 0. And this is what the graph looks like. So you can see the derivative does not exist here at 0, right? It's -1 all the way until here, and it's +1 starting just past here. So there is no value at 0. Now, the derivative is a function. That's what we've been talking about here. And since the derivative is a function, you can actually also take its derivative. And you can do this as many times as you need to, because every derivative you take just produces a new function whose derivative you can also take. So we have what we call higher derivatives or higher order derivatives. And the notation that we use for these higher derivatives, for the second derivative, that's the derivative of the derivative, we use f double prime of x. Or if we use the Leibniz notation, it's d squared y dx squared, okay, to denote that it's the second derivative. Third derivative, we get triple prime, or d cubed y over dx cubed. Once you get past the third derivative, writing the primes tends to become a little cumbersome. We don't want to have to write primes over and over and over again. So we use this parentheses notation. It looks like an exponent, but it's not. So this would not be f to the fourth power. This is the fourth derivative of f. This is where the Leibniz notation can be very helpful because it's very consistent. It's the same thing repeated, just with the number increasing. But both of these are valid derivative notations. And then obviously for the nth derivative, anything above that, we would just use whatever that number is. So you could take the 100th derivative and it would just be f parentheses 100 up here in the power of x, or d to the 100 y over dx to the 100. Okay? And that's certainly preferable to writing out 100 primes on a 100th derivative notation. In terms of our application, we've been looking a lot at position and velocity. So position is the function s of t. The derivative of position that we've talked about a lot is the velocity. The rate of change, or the derivative of velocity, is acceleration. And the derivative of acceleration, or the rate of change of acceleration, which we don't see come up too much, but it does have its own name. This is called the jerk. So kind of that idea, like your acceleration is changing at an increasing rate or at a decreasing rate. If you think about it in terms of a car, right, your position is where you are while you're driving. The velocity is, like your rate of change, how quickly you're going, like on your speedometer, that's your miles per hour. The acceleration is how hard you're stepping on the gas pedal, right, or on the brake pedal. If you step on the brake harder, you're going to decelerate faster. If you step on the gas harder, you're going to accelerate faster. The jerk is the rate of change of that acceleration. If you slam on the brake, you notice what you do, like you jerk forward. You kind of like fly forward in your seat a little bit. That's basically the jerk. So looking at an example that we've already kind of started here. Earlier we found f prime of x for this function. Now we're going to find these next few derivatives. So for f double prime of x, that is f prime prime of x. Right? It's the derivative of the derivative. So we're starting here at the derivative now. So this is going to be the limit as h approaches 0 of f prime of x plus h minus f prime of x all over h. So that's going to be limit of 3 times x plus h squared minus 1 minus 3x squared minus 1 all over h. We get, so 3x squared plus 6xh plus 3h squared minus 1 minus 3x squared plus 1 all over h. Cancel, 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 cancel. Common factor of h in each of these. Factor out and cancel. So we're left with 6x plus 3h. As h approaches 0, this whole term is going to turn into 0. So we're just left with 6x. That is f double prime. That is the second derivative of this function, right? Or the derivative of the derivative. And then this pattern continues. So for f triple prime of x, so that would be the derivative of the second derivative, so f double prime prime. So this is the limit. You'll notice these derivatives are going to get a little bit easier as we go along here. So that's f double prime of x plus h minus f double prime of x all over h. So that's the limit as h approaches 0 of 6 times x plus h minus 6x all over h. So we get 6x plus 6h minus 6x all over h. 6x's cancel, h's cancel. We just have limit as h approaches 0 of 6, which the limit of a constant is just that constant. So f triple prime is just 6. So that's the third derivative of that function. And then the fourth derivative of x, so that's f triple prime prime, right? So the derivative of the third derivative. So that's the limit as h approaches 0 of f triple prime of x plus h minus f triple prime of x all over h. The nice thing about this one is there are no x's in this formula for us to substitute in for. So f triple prime of x plus h and of x are actually the same thing. It's all just 6. So that's 6 minus 6 over h, which is 0. And then we would kind of get stuck there. If we tried to do any further differentiation, you would just keep getting more and more zeros as we went along. But again, these higher order derivatives, the second, third, fourth, etc., it doesn't change anything about how we take the derivative. It just gives us more of kind of these same processes. But that brings us to the end of section 2.8 and to the end of chapter 2.